Okay, welcome everybody. Welcome back. And it's my pleasure to introduce Constance Schober. And she's going to talk to us about numerical investigation of nonlinear damped spatially periodic breathers and the emergence of soliton-like rogue waves. Connie.
Okay, thank you. And I want to thank the organizers for this really wonderful workshop. I also wanted to acknowledge my co-author, Alvaro Islas, on this project and longstanding collaboration with Annalisa. Okay, so in deep water, rogue waves may appear in a regular wave field due to the modulation instability of the background state and nonlinear focusing of uncorrelated waves in a localized region of the sea. And so the nonlinear Schrödinger equation is one of the simplest models capturing the modulational instability and self-focusing of deep gravity waves. It possesses large families of special solutions which exhibit the qualitative properties of rogue waves. These solutions are localized, transient, and steep, and they've been studied as possible models. These include the peregrine type rational solutions that decay polynomially to the ground state in space and time, and the in-phase solutions proposed by Honorato and Osborne. Also, heteroclinic orbits of unstable Stokes waves, also known as spatially periodic breathers, and finally, the heteroclinic orbits of unstable in-phase solutions. And so these references that are given are really in reference to when they were proposed as models for rogue waves, not for when they were developed or derived as solutions to the NLS equation. So let's look at these spatially periodic breathers of the NLS. So it's well known that the Stokes solution is unstable to long wavelength perturbations and has in unstable modes if you satisfy the appropriate relation with A and L. And each of these unstable modes has a heteroclinic orbit characterized by the wave number mu sub j. And in these heteroclinic orbits can be obtained by a Becklin transformation. And in the first two plots, you see two distinct single mode SPBs that are associated with the plane wave. And multi-mode SPBs can be obtained. Oops, are you still seeing it as a full screen? Are you still seeing the slides as a full screen? Hello?
No, Connie, not anymore.
So, okay, so it's now, can you see them at all?
On the left side. But,
okay. Okay. I have to go back to, to view slideshow. Okay, all right. It's just, okay. It just has a button at the bottom of the screen, and I thought that it could be eliminated, but I guess not. Okay. So these multi-mode SPBs can be obtained by iterating the Becklin transformation, and the form of a two-mode SPB is there. And you see that it depends upon these parameters, rho and tau. And the third plot is showing a two-mode SPB where the parameters have been chosen so that the modes are excited simultaneously and coalesce and spike up to this maximum amplitude of the two-mode SPBs. So the nonlinear Schrödinger equation is just the leading order approximation in describing deep water wave dynamics. And we saw yesterday in the talk of Catherine Salim, she discussed the Disti equation, that it's obtained by retaining these terms through fourth order and an asymptotic expansion for the surface displacement. And so if you look at the equation towards the bottom of the slide, you see that when beta is equal to 0 in this equation, you essentially have the Hamiltonian version of the Disti equation. And so you have the higher order terms, which are giving you your higher order dispersion and nonlinearity, and this signature of the Disty equation, the Hilbert transform term. And so the Disty equation is used widely because it's effective with steep waves. And earlier numerical simulations using the Disty equation, they were able to capture the chaotic long time evolution of the modulation instability that was observed in laboratory experiments by Hammack and Henderson. And so another phenomena related to the modulation instability is frequency downshifting. And this occurs when the energy is transferred from the carrier wave to a lower sideband when it becomes permanent. And this has been observed in both laboratory experiments and in ocean waves. And there has been a continual attempt to understand downshifting and model it from the time it was first observed by Yoon and Lake in 75 to today. And so, you know, at the bottom, I have a reference, a relatively recent reference to Corridor, Henderson, and Butterfield. But of course, there are many, many others, you know, that have been working on this. And so, one of the natural it's natural to include damping or into the model for describing frequency downshifting, since it typically there's a significant decrease in the energy in the system. And so unfortunately, though, linearly damped higher NLS does not exhibit permanent downshift. And so a more realistic exploration of deep water wave dynamics can be achieved with a nonlinear damped higher order NLS equation. And here we introduced this beta term, which models then damping of the wave-induced mean flow. And the important takeaway was that from the numerical experiments, we were able to show that nonlinear damping does allow for frequency downshifting. And in later studies, you know, in a comparative study, the nonlinear damped higher order NLS was shown to be the most accurate model for predicting the permanent downshift observed in a set of laboratory experiments. And just so you have an idea, you know, a rough idea of the effect of this damping term, you know, here's the spatial profile of the amplitude of U at some time t star versus its, you know, the nonlinear damping, the beta term. And so you see the damping term is, you know, given by the red dashed line. And so you see that the nonlinear damping is essentially effective only near the crest of the envelope, and that steeper waves result in stronger damping. And so this nonlinear damping is a very localized in space and time type of damping. It's not uniform or constant in time like you would have with linear damping. So it's able to achieve this permanent downshift. Okay, so that's just background for our choice of the equations. And so what we are interested in today is to investigate the stabilization of the SPBs and the related rogue wave activity in the framework of this nonlinear damped higher order NLS equation. And so the initial data is generated using exact SPBs of the NLS equation at time T0, big T0. And so what we will be doing is varying T0 to allow for initialization at different stages of the development of the modulation instability, and will vary the number of unstable modes of the background. And so in the spirit of earlier work by Ercolani, Forrest, and McLaughlin, we will be using the Floquet spectral theory of the NLS equation to characterize the perturbed dynamics in terms of nearby solutions of the NLS equation. And so the questions that we are interested in addressing are: what are the distinguishing features of the damped higher order NLS flow as determined by the Floquet spectrum? which integrable instabilities are excited by the damped flow, and which NLS states are relevant to modeling the perturbed flow. And also, how does the damped higher order NLS evolution and its Floquet spectral decomposition depend upon T naught, the rogue wave activity? So we begin by recalling that the NLS equation is the compatibility condition of the Zakharov-Shabbat system, and that general periodic solutions of the NLS can be represented in terms of a set of nonlinear modes whose stability is determined by the Floquet spectrum of the spatial part of the Zakharov-Shabbat system. And so to determine the Floquet spectrum, we let psi be a fundamental solution matrix of the Zakharov-Shabbat system. And then the principal object in Floquet theory is the Floquet discriminant delta, which is the trace of the monodromy matrix and which governs the growth of the eigenfunctions as they're mapped across the period. And our spatial operator Lx is not self-adjoint. And so in this case, the spectrum is given by all complex lambda such that delta is real and bounded between plus and minus 2. And so the Floquet spectrum consists of bands of continuous spectrum and the discrete set of periodic antiperiodic spectrum where delta is equal to plus or minus 2. The simple points of the discrete spectrum are the endpoints of the bands of spectrum. And so they're in this figure, they're given by the little dots or bubbles, indicated by the dots or bubbles. And located within the bands of spectrum are two important spectral elements. You have the critical points of spectrum, which are determined by the condition that d delta d lambda is equal to 0. And you also have the double points of the discrete spectrum, where these are degenerate elements of the discrete spectrum. And so there's an important difference between real and complex double points. The real double points correspond to stable inactive modes, and linear instabilities of periodic solutions typically correspond to the complex double points. And so these elements of the spectrum are illustrated for a Stokes wave, given here along with its discriminant delta. We see that the continuous spectrum is the entire real axis, and a band along the imaginary axis ending at the discrete simple points plus and minus IA. You have a infinite number of double points given as follows, and there's a infinite number of real double points, but a finite number of complex double points. And the number of complex double points is the same condition, the same Benjamin Fair condition for a mode to be unstable. So you have then in unstable modes and in complex double points. And as we mentioned before, each of these complex double points, you can construct a heteroclinic orbit using a Becklin transformation. And the important feature is that the Becklin transformation is isospectral. So the spectrum for each of these single mode SPBs that was shown before, and the spectrum for the Stokes wave, and the spectrum for the double the two mode SPB, the spectrum is the same as given there. Okay. Okay. So in the higher order NLS experiments, the complex critical points become important since the higher order terms break symmetry. And so in figures A and B, we have a standing wave, even three-phase solution, and it's associated what's colloquially called the cross state in the spectrum. And so there is there's a critical point in the spectrum where the two bands intersect transversely, and you find that if you take small even perturbations of this data, all that you're going to do is produce a cross state with a different band length. And for this perturbed initial data, U naught and U delta will stay delta close as time evolves. And however, if you look at asymmetric perturbations of initial data, they will split the critical point and you obtain a left or right traveling breather depending upon whether the upper band of spectrum is in the right or left quadrant. And in this case, U naught and U delta diverge as time evolves. And you can see the growth in the H1 norm of the difference of the difference of U delta and U naught here. And so the question here is that, traditionally complex double points are associated with these linear instabilities, but there's some type of the numerical experiments suggest that complex critical points are related to some type of weak instability. And so what's the exact nature of the instability? So to corroborate the numerical experiments, we examine the spectrum for small time for damped SPB data. And to do so, we find first the linearized initial conditions for the SPBs, and then we find the following first order approximations to the nonlinear damped SPB data that's valid for small time. And so you see from this data that this data is asymmetric. And an important point of the form of the data is that the thetas and the phis are not equal. And all of the coefficients are functions of H and of the nonlinear damping parameters epsilon and beta. And so for simplicity, we set epsilon equal to epsilon sub s tilde, and we suppress the explicit dependence on epsilon, beta, and H, and we have initial data of this form. And where the U1 is of the form F sub I plus QF sub J, and Q can be either 0 or 1, depending upon whether you're looking at a 1 or 2 mode SPB. Okay, so you then assume a perturbation expansion for lambda sub n and v sub n, and add for the the eigenvalues and the eigenfunctions, and you find that at order epsilon you have this correction lambda sub n1, and you see right away that if n is not equal to I or j, that there is no first order correction in the eigenvalue. And if n is equal to I or j, we have this expression for the first order correction. And again, we have that theta n tilde is not equal to phi sub n tilde plus or minus m pi. So one of this perturbation analysis can be carried to higher order. And so one of the results is that if you are examining a single mode SPB, then at order epsilon n, only the double point lambda sub nj will split, and all of the other double points lambda sub L, where L is not equal to MJ, will not split. So for example, if you're looking at U2, which is built off of the second double point lambda sub 2, then lambda 1 will not split under the higher order NLS perturbation. And this is a short time. This is a short time analysis, but it actually carries through for the duration of the, you'll see that it carries through for the duration of the numerical experiments. And so for a 2-mode SPB, both complex double points will split at order epsilon. And again, the perturbation is asymmetric. And so lambda, the double point splits asymmetrically into these two disjoint bands of spectrum. and create this right or left traveling mode, depending upon whether lambda plus the upper lambda is in the right or left quadrant. Okay, so now for the setup of the numerical experiments, the N unstable mode regime refers to the solutions that are initialized near a Stokes wave with N unstable modes. And again, the initial data is generated using exact SPBs of the NLS equation at T naught, and we're varying N and T naught. And in all the experiments, the perturbation parameters are epsilon equals 0.05 and beta equals 0.2. So the principal diagnostic is the Floquet spectral decomposition of the nonlinear damped data, and it's computed at each time t in steps of delta t equals 0.1. The presence of both complex critical points and double points is monitored, as well as the links of the bands of spectrum in the upper half plane associated with the dominant modes. And so we are using the term a soliton-like state, or we have the soliton-like criterion, that when tiny bands emerge, we view that the corresponding modes of the N-phase solution behave qualitatively like a soliton, that they have this soliton-like structure. And so if one or two of the band lengths satisfy, gamma less than 0.025, then the spectrum is said to be in a 1 or 2 soliton-like configuration. And the motivation for the terminology, to just consider the example of the three-phase solution. And in this case, you have your elliptic modulus with K and kappa. So for the conoidal functions that depend upon time, it's kappa, and the conoidal functions or the elliptic functions, more generally the elliptic functions that depend upon x, the function or the parameter is K. And so the relationship between K and kappa is given there. And so as kappa goes to 1 and K is going to 0, your solution limits to a single mode SPB, and the gap closes down to a double point. And in otherwise, as in the opposite limit, as kappa goes to 0 and K goes to 1, then the solution limits to a soliton, and your band lengths shrink to the discrete points at plus or minus IA. The several other diagnostics are used. We are looking at the rogue wave criterion, where we determine that rogue wave events, to determine the rogue wave events, we examine the strength function, and here the significant wave amplitude H sub s, it's this ratio of the maximum in x at time t of the amplitude u over the significant wave amplitude. It's defined, the significant wave amplitude is defined as the average wave amplitude of the highest 1/3 of the waves. And so a rogue wave occurs at T star if S of T star is greater than 2.2. And so to complement the spectral analysis, we examine the growth of small perturbations in the SPB data, and we measure the evolution of the H1 norm difference of U naught and U delta. And this is given by D here. Okay, so you'll be seeing plots of D. Okay, so just to sort of set the framework and the notation, we start with this case isn't as interesting as the two unstable mode regime, but we're looking here at U1 and the 1 unstable mode regime. And here, under the nonlinear damped flow, you have initially, well, before we have the nonlinear damping, initially, what you're seeing here is the band of spectrum on the imaginary axis with one double point. And so under nonlinear damping, lambda sub 1 splits asymmetrically into lambda 1 plus or minus at order epsilon. And when this is consistent with the short time perturbation analysis of the spectrum. And we see that U1 here in figure A, the amplitude of U1, it exhibits regular behavior and evolves as a damped right traveling breather. There are no rogue waves in the evolution of U1. And the spectrum persists in a right traveling breather state for the duration of the experiment. So complex critical points or double points do not occur in the spectral evolution of U1 in the one unstable mode regime. And you see that there's no significant growth in D, in that H1 norm of the difference, which is consistent with the prediction of stability from the evolution of the spectrum. And so U1 can be characterized as a continuous deformation of a traveling three-phase solution. The amplitude of the oscillations decrease and the frequency increases until you have these small, fast oscillations about the damped Stokes wave, which you saw in the, which you can see in the surface there. Okay. So what about, as I say, this is a more interesting regime, the two unstable mode regime. So we're starting with U1. And in this case, initially, you have two complex double points, which are indicated by the red X and the blue box here. And so damping splits the first double point at order epsilon and the second point at order epsilon squared, and they're both split asymmetrically. Again, consistent with the short-term perturbation analysis. All of the short-time perturbation results, all of those short-time numerical results are consistent with the perturbation analysis. And so subsequently, the two upper bands decrease in length and they detach and move away from the imaginary axis. And so at T approximately 5, which you see in the third plot here in figure D, I guess it's the fourth plot, sorry. In the fourth plot, you see that one of the band lengths has, or satisfies the band length in the right quadrant satisfies this condition for, a soliton-like structure. So, this reflects the emergence of this waveform close to a soliton-like structure. And the soliton-like state satisfies the criterion of a rogue wave, which you can see here. It's visible here in the strength plot. This is the strength plot at T about 5. And so the complex critical points occur intermittently throughout the evolution of the spectrum until T is about 14.7, and you have here one of the last critical points that are formed at T equals 14.3. And so at T about 15.2, a one soliton-like state again forms and a more pronounced rogue wave is observed. And so the last soliton-like spectrum and last rogue wave occur at T equal 33.8. And so this is probably more clearly visible on the third plot here. The rogue wave events are determined from the strength plot on the prior page. The rogue wave events are determined from the strength plot, and they're given by the red dots on the t-axis of this band length plot for gamma 1. So this is a plot of the band length gamma as a function of time. And so what you see is that when a rogue wave is observed in the strength plot of U1, that the spectrum is in this soliton-like configuration. And the other in feature that is of note is that the difference, the D of T, it saturates around T equals 15.2, and this is an agreement with the stabilization time that's determined by the last critical point in the nonlinear spectral decomposition of the solution. So again, there are no double points. After t equals 0, you have the two double points, but then they immediately break, they immediately split, and then you don't have any subsequent double points in the spectrum. Yet you have growth in D of t. Okay. So, so the next example in the two unstable mode regime is for U2. U2 is is another single mode SPB, and it's associated with the second complex double point. It's built off of the second complex double point, and so I didn't repeat the spectrum initially. It's exactly what you had here, as we discussed before, with the Beckland transformation being isospectral. The spectrum for U1 and U2 is identical. And so so in the surface plot, you see that U2 is a damped traveling breather, and it exhibits this regular behavior in contrast to that transient irregular behavior that you saw in U1 in the two unstable mode regime. And the small time perturbation analysis predicts that for U2, damping will only split the complex double point lambda sub 2 at order epsilon, lambda 4 at order epsilon squared, etc. And you see that in the spectral plots. So here on this upper band of spectrum in the right quadrant, you see a larger X, and that larger X indicates the first double point, which does not split. It just basically translates along the band of spectrum and never splits. But there is a distinctive feature of the spectral evolution for U2 that's different than if you had, say, linear damping in the problem, the linear damped higher order NLS. And that's that the solution actually gains an unstable mode, which corresponds to lambda 3 having moved from the real axis onto this upper band, onto this band of spectrum in the upper half plane. So you see that here, that aside from having the lambda, the double point over here on the first band, you also have an additional complex double point. And so, these, and here you also can clearly see the double points on the two bands here in the left quadrant and the right quadrant. And so there are no rogue waves observed in the evolution of U2, but you do have these complex double points, which would indicate instability. And so the thing that's surprising is that since the first double point remains intact, we would have expected to see growth in the difference of the nearby trajectory, the nearby initial data that evolves. We would have expected to see growth in this initially. And if you had, for example, linear damped higher order NLS, you would have seen a similar situation where lambda, the first double point does not split, and you would have seen a much more striking growth in the difference of the nearby initial data. And the speculation is that if you look at a Fourier decomposition of the data, there's a permanent downshift in the spectral peak. And the spectral peak is the index of the Fourier mode of maximum amplitude at t about 40. So you see that you have a downshift from the 0th mode to the second mode at around t equals 40 due to the nonlinear damping. And so nonlinear damping seems to inhibit the growth of the instabilities until the spectrum has downshifted. And so after it downshifts, then you see the growth pick up, the instability start to be excited, and you have to then wait until the solution is sufficiently damped that the instability saturates there. So the Fourier mode plot for U2, this is a perturbed initial data. So this is actually the initial data for U2 plus delta cosine mu 1x. So in this plot, this Fourier mode plot for this initial data, it shows that even when the first mode is seeded and you've put in this perturbation related to the first mode, that downshifting appears to inhibit its growth, which is expressed at higher order. And the red, so the black curves corresponds to the 0th mode, and the red dashed line corresponds to the -2, k equals -2. But for k equals -1, then you have that it doesn't actually have significant growth until after 100. So the question is, what's the role of downshifting in inhibiting the growth of instabilities? Okay, and so our last example is the case of the coalesced two-mode SPB U12, and again you have the two complex double points initially, and now since it's a two-mode SPB, both lambda1 and lambda2 are split asymmetrically, and in this case, complex double points nor complex critical points appear for t greater than 0. And so these two tiny bands, these are even smaller than you saw in the previous case. These two tiny bands of spectrum pinch off from the imaginary axis and enter a two soliton-like spectral configuration at t equals 3.5. So you see the two tiny bands there. And it's in this two soliton-like state for an extended period of time from about 3.5 to 18. And the spectral bands then enlarge, and the spectrum has the following pattern, that you have both complex double point splitting and going to a two soliton-like state, then a one soliton-like state, and then you have this generic in-phase spectrum. So after, this fourth plot here is at t equals 27, and so you can see you only have the one small band of spectrum. The other band has enlarged, and then eventually they both enlarge, and you have that generic in-phase state. Okay, so the rogue waves are determined from the strength plot and are given by the red dots on the t-axis of the band length plot. And so here we're now plotting the band length for both gamma 1 and gamma 2. We only plotted the band length for gamma 1 before because gamma 2 was never small to begin with, so or small throughout the experiment. So here we're plotting the band length for both bands, and you see that when a rogue wave occurs here, that the spectrum is in either a 1 or 2 soliton-like configuration. And as I said, said before, that complex critical points and double points don't appear for t greater than 0. And so you see here in this plot that there's no significant growth in the difference of u delta and u naught. And so the nearby trajectories remain close for t greater than 0. And just as a rough comparison, if you let lambda 1 and lambda 2 be the midpoints of the bands of spectrum that pinched off, then the two soliton analytical solution obtained using lambda 1 and lambda 2 appears structurally in good agreement with near the peak with the nonlinear damped SPB U12. Okay, and so that was for specific T naught. And so what's the dependence of the rogue wave activity on T naught? And so here, what we are plotting is the time a two soliton-like spectrum is first observed, and that's given by the blue line, and then the time at 2 soliton-like spectrum is last observed, and that's given by the dashed red line, and the time of 1 soliton-like spectrum is last observed. It passes from a 2 soliton state to a 1 soliton-like state, and so the dashed line here also corresponds to the time your 1 soliton-like state is observed. And so finally, the purple dashed line is the time a rogue wave is last observed. And the T naughts that were used varied from -5 to, this is the dependence on T naught that's being shown. And so T naught's varying from -5 to 0, and T naught is incremented in steps of a half. And what you see is that the evolution of spectrum has the following pattern for all T naught, that you have a 1 or 2 soliton-like state, which transitions to a 1 soliton-like state, and then to this generic N-phase spectrum. But the main observation is that not the main observation, but one observation, is that for the coalesced 2-mode SPB, when T naught is between -5 and -1.5, so you're there initializing in the early to middle stages of the development of the modulational instability. In that case, rogue waves emerge when the spectrum is in a 1 or 2 soliton-like state configuration. And so a question is, as these band lengths shrink to 0, is there a limiting wave amplitude, and can the nonlinear damped solutions with these tiny bands, can they be analytically expressed in terms of solitons? And so as you vary T naught between -1 and 0, so you're initializing near the peak, then in this case, the last rogue wave can occur sometimes significantly after the spectrum has left the soliton-like state. And an example is given here for T naught equals 0, and you have a rogue wave around 47, but the spectrum is not in a soliton-like state. So there is some other mechanism for rogue wave development in these cases. Okay, so I think that's more or less it. And so finally, the conclusions are that the novel features of the nonlinear damped dynamics are that for U1 and U12 initial data in the 2 unstable mode regime, tiny bands of complex spectrum pinch off in the Floquet decomposition of the damped data, and it reflects the breakup of the SPB into a waveform close to a 1 or 2 soliton-like structure. And so for solutions that are initialized in the early to middle stage of the development of the modulational instability, all rogue waves occur when the spectrum is in this 1 or 2 soliton-like configuration. And when the solutions are initialized as the modulational instability is saturating, then rogue waves may occur after the spectrum has left a soliton-like state. In examining U2, the single mode U2, it gains for a time in unstable mode as lambda3 moves from the real axis into the upper half plane, and the growth of instabilities may be delayed and expressed at higher order due to permanent downshifting. And so these are just a repeat of the open questions that we had before of what's the nature of the instability related to complex critical points, what's the role of downshifting in inhibiting the growth of instability, and is there a limiting wave amplitude as the spectral band lengths shrink to 0, and can this limiting behavior be analytically expressed in terms of solitons? Okay, so that's it. Is there anybody still there?
Yes, we're here, I think.
Okay, so that's it. Are there any
Connie, can you hear me?
Yes, yes.
Okay, sorry about that. Thank you for your great talk. And I now open the floor for questions. So I have a comment,
Yes.
which is maybe Marco Bertola is not here, but last week or several weeks ago, he was showing us formulae that were taking limits of finite band solutions and seeing soliton-like formulae coming out of that. So it might be related to the open question, the last one there.
Yeah. I am excited to be able to have the chance to talk to you guys while I'm here about it. Yeah, it sounds like that it could be very similar. Yeah.
Other comments or questions? Okay, so then let's thank Connie again.
Okay.